Yeah, okay. So yeah, it's my pleasure to welcome Kevin Webster, who'll be reading, but maybe he doesn't like the word reading, coordinating this reading session.
No problem with word reading. Word reading is fine.
Yeah, okay, yeah. So that a paper on a priori estimates of the population risk for two-layer neural networks. Yeah, thank you.
Yeah, okay, thanks, Bamidin. So Bamidin asked me to if you'd be interested to start a reading group related to deep learning. So this is a paper I've been looking at relatively recently, which I thought may be interesting. So it's a short disclaimer though, so I wanted to make a small disclaimer in the beginning. So in terms of dynamical systems, this paper is not really concerned with dynamical systems. This paper is more concerned with convergence estimates of deep learning models. There is a follow-up paper to this one that I know of, but I haven't looked at yet, which is extending these kinds of results to deeper networks. And there they relate the results to ODEs, or they're using ODEs in the theory. So it may be interesting if there's interest to take a look at that one further down the line. But I'll start with this one for now, in any case, and see how we get on with it. Just trying to work out how to share the. Okay, here we go. Hang on. Sorry, I'm a bit of a Zoom novice, so give me a moment. Can everybody see this?
Yes, thank you. Yeah.
Okay, nice. All right. Okay, so I think the session was advertised for 2 hours. I'm not going to take 2 hours. I'll certainly take a lot less than that. Basically, what I thought might be quite nice to do today is just to run through this paper and talk about the high-level results really that are in there, and just kind of get a feel for what the paper is about without going through any of the details in particular. So hopefully we get a good understanding. And by the way, I'm very happy. In fact, I'd like to encourage interruptions. So this isn't a talk. I don't want this to be a talk really. This is just I'd like it to be more of a discussion than anything else. So please do feel free to stop me and interrupt. And if something is not clear, then we can talk about it. Okay, so this is the paper. So the title A Priori Estimates, first of all, probably needs a bit of clarification, and well, maybe all these terms, population risk as well, and so on. The key equations, I think, to understand that are given on this page here. Can you all see my cursor, by the way?
Yes, yeah.
Yep. Okay. So these two equations describe what they mean by a priori, as opposed to a posteriori, as you can see here. So a priori basically means that the estimates are given of this form, and what we're interested in doing here is getting convergence estimates for the neural network model. So in this equation, you can think of f sub n, f hats of n, as being the neural network, and f star is the target function that we're trying to approximate with the neural network. And we're assuming that the function space that the neural network is operating in covers the target function. Okay, so that's an important underlying assumption throughout this paper. So if that's the case, then we can find parameters of the neural network that converge to the target function. And these kind of estimates basically tell us how fast we do that in terms of the number of data examples. So n here is the number of data examples, c and alpha are just constants, and as I say, f star is the target function. So an a priori estimate would be something like this, which is given in terms of the target function on the right-hand side. And as you can see, the only difference between this one and this one is that this estimate is given in terms of the neural network function on the right-hand side. And there's, I suppose there's plus and minus points for both of these. So in terms of the a priori estimates, this is nice because the target function is fixed. So it doesn't matter how many data points you have or your training algorithm or anything like that. The target function is fixed. So the right-hand side here, this is a constant that will stay constant for any number of data examples or anything else that you may choose to vary. But you don't know what it is, of course. You don't know what the target function is. So you don't know how big this norm is of the target function. So that's the potential drawback. This norm may be very large, in which case this bound might become vacuous, might become useless. On the other hand, for the a posteriori estimate, the right-hand side, we've got this, the neural network norm on the right-hand side, and this is something we can calculate. So we know exactly what this is. So we can give a firm bound, if you like, on the right-hand side. But the issue is that, of course, this varies for different number of data points. So this isn't something that we have necessarily that much control of. This might blow up as n goes to infinity or whatever. So this is a bit of an issue with the a posteriori estimates. So this paper is concerned with the first one, with the a priori estimates. Good. Unless there's any questions, I'll
yeah, norm 3, what that means?
Yeah, say it again, sorry.
Norm 3.
Yes, so these are undefined at the moment. So he just says here, these just denote various norms. So this is very non-committal at this point. So we don't know what these norms are. This is meant to be an abstract idea of the kinds of estimates that we might want to consider. So suppose we have some norms, 1, 2, and 3, then we want to write down estimates of this kind of form. So we'd assume that we know what these norms are, but this is quite an abstract equation at this point. We haven't defined what they are. As we get down to the theorems later on, then we will define what the norms are that we're going to be using for these estimates. Okay, so what does he say about the main contributions of the paper? So establishing the a priori estimates, as we just talked about, of the population risk. I'll talk in a second about what that is. For learning 2-layer neural networks. So I'm assuming everyone has some level of familiarity with neural networks. Is there anyone who hasn't come across neural networks before? We know what they are? No? Okay, so in this paper, we're considering 2-layer, which basically means a single hidden layer. So this is the setting for this paper. It's the simplest case in which you can give these kinds of estimates. A follow-up paper, as mentioned before, does do deep neural networks where we consider many layers. But this paper is just about a single hidden layer network. So main contributions establishing the a priori estimates of these 2-layer neural networks with explicit regularization. So this is a point he talks a bit more about in section 2 as well. So the algorithm, or maybe not algorithm, but the loss function that he's defining for this has an explicit regularization. And so he obtains these bounds by adding a penalty term, essentially, to the loss function. And this is how he gets these bounds. And that's an explicit regularization because it's a term that you're adding to the loss function, as opposed to implicit regularization, which is things like early stopping. People have heard of this thing before, or different types of training algorithms, stochastic gradient descent, things like that, which also have a regularization effect, but are implicit rather than explicit. So he does say at the end of this paper, one critical point that he makes at the end of this paper is that in practice, people tend to use implicit regularization techniques, and this paper hasn't got anything to say about that at all. And this is quite poorly understood in general. But this paper is purely about
any connection to the norms?
For the explicit regularization
and norm, are they connected or not?
Yes, they are. They are. Yes. So
okay.
So there's a bit of building work outside. Give me 1 second. I'm going to close the window.
All right.
It's every time you're on a meeting. That's when the builders start. Yeah, the question was about norms. So yes, that it is related. So the regularization that he uses in this paper is using something called a path norm, which is some measure of complexity of the neural network. And he uses a few norms in different places, but yes, that is the norm that he uses for the regularization in particular. The bounds, by the way, that we prove for the population risk, these a priori estimates do use other norms. So in particular, this paper uses something called a Barren norm. The function space that these networks are operating in is this Barren space, and we'll come to this. We'll come to this quite shortly. So there are a few norms floating around in this paper. The second point he writes on this page is he makes a comparison between neural networks and kernel methods using these a priori estimates. So this is something I found quite illuminating actually when I read this paper. I thought it was a very nice a nice contribution, a nice part of the paper. So it does help to explain to some extent the benefits, I suppose, of using neural networks over kernel methods. And in a nutshell, the argument is that using neural networks, you are able to essentially learn what the kernel is. You have some sort of control over learning the kernel. So you can definitely interpret the neural network model in the end as a kind of kernel method, but it's where you're able to learn the kernel. I think this is quite a nice insight. I found this quite a nice insight in the paper. He also does, as you can see, reference some future papers here. So this is part of a series of papers. This is the only one I've read, but the following one, which looks at deeper networks, I'd be interested to take a look at that as well. And maybe we can do this as part of the reading group, but again, if there's interest. Section 2, I'll skip relatively quickly through this. So he talks about some related work. In this section, particularly about related papers that have similar kinds of estimates. And I think the main point here in section 2.1 is he references other papers that also use explicit regularization as a means to obtain these convergence estimates, and lists a few of these rates and compares them with the one obtained in this paper. One main difference, as you can see in this table, appears to be that the other papers don't consider the case of over-parameterization. So this is where we have a neural network with many layers, many units in the hidden layer. There's only one hidden layer, but it can be a very wide hidden layer, so many neurons in that hidden layer, to the extent that the number of neurons, which we call M in this paper, is much larger than the number of data examples, which here he calls N. So in the case where M is much bigger than N, we're in this over-parameterized regime, where in principle, you'd expect that the model is so powerful in relation to the data set that it would have the ability to significantly overfit to the data set. And you may end up with a very bad generalization gap. So that's one difference between the papers he references here and this one. So in this one, he does consider the over-parameterized regime, which is interesting because this is often the case that we're usually working in practice. So the neural networks very often have got millions of parameters, and you may be working on, let's say, tens of thousands of data points. So the over-parameterized regime is very standard, I would say. And this is the regime that he's considering here. And so key to not overfitting is, of course, this idea of explicit regularization. And a kind of central part of the proofs in this paper are about choosing the regularization parameter with the right rate in terms of the number of data examples. So it shows that with a very carefully chosen regularization parameter, you can control the size or the complexity of the model in such a way that it doesn't overfit the training data, even as M, the number of neurons, goes to infinity. So that's section 2.1, just talking about some related papers there. Section 2.2, I think I'll skip over this one, but this is again talking about related works that consider convergence estimates, but in the case of implicit regularization. So things related to SGD or early stopping or things like that. So I'll skip over this right now. Are there any other questions? Otherwise, I'll leap into the preliminaries and start looking into some of the notation and objects used in the paper. Okay, so I'll go through the preliminaries, and then once we've got the main definitions of the objects that we're interested in, I'll jump to the statement of the theorems so we can see what's actually shown in the paper. But we need to go through this section first. So the problem shown at the top here is we have n training examples, and we're considering just inputs and outputs, x and y. And this is a regression problem that we're thinking about here. So y would be just a real value that we're trying to predict given an input x, and x is d-dimensional. So these are IID samples, standard kind of assumption. Here's our underlying distribution, rho, which is fixed but unknown. This is the target function f star we saw above that we're interested in. So in principle, the labels y could be noisy, in which case we're defining f star, the target function, to be the expected value of y given x. Later on, there are two theorems, one for the noisy case, where you do have that noise in the labels, and one for a noise-free case, where there is no noise. This is the form of the noise, so this is an additive noise. If the noise exists, then we're just adding some independent random variable to the target function f star, which has got an expected value of 0. and a couple of simplifying assumptions, which I don't think is really necessary, but it helps with the proofs to kind of keep things nice and compact. So he's assuming that the input data is constrained between the interval -1 to 1 in d dimensions, and also he's constraining the output of the target function f star to lie between 0 and 1. As I say, I don't think these are essential. As long as they're bounded, then everything would work just fine. But this makes things a bit easier, a bit nicer to read in the proofs. So equation 3.1 should be kind of familiar. This is the equation for the two-layer neural network. You may or may not have seen it written down in this form, but this is basically what this is. So we have some inputs x here. The parameters of the neural network are wk and ak. So wk would be the weights for the from the inputs to the hidden layer, and ak are the weights from the hidden layer to the output. And sigma here is denoting an activation function, which he assumes in this paper to be a scale invariant activation function. So something like a ReLU would satisfy that, or a leaky ReLU. So this is the condition here in particular that he wants the activation function to satisfy. This point, I actually don't know how essential this assumption is for the results in the paper. So I haven't dug into that really. I don't know if the results would still stand if you use, say, a sigmoid or a tanh activation function or something like that. So in any case, he assumes this is scale invariant, so we can think of this activation function as being a ReLU activation function. And also he assumes it's Lipschitz continuous with Lipschitz constant 1. Well, oh yes, so you may be used to seeing a bias term in here. So often you'll add a bias before you pass it through the activation function. So he's writing in this form again just to keep it simple. Without lots of generality, we can do this because we can just extend the inputs x with an extra constant feature equal to 1, and then the bias term becomes absorbed into this wk. So this also covers the case where you do actually use a bias term there. Okay, good. Any questions on this? Good. All right. So then I spoke about this before. So we're going to say the network is over-parameterized if the network width m. So we have, as you can see here, m neurons in the hidden layer. So if the network width m is larger than the number of data examples n, then we're going to call this model over-parameterized. And this is, okay, this is a technicality. This is not so important, but he's going to constrain the output of the neural network function to be between 0 and 1. So we just assume that. So it's always within that range. Again, this just makes things a bit easier for the proof later on, but this is not an important point.
I guess you defined it, but what is population risk in this paper?
Yeah, I'm almost there. So it's this object right here. So I haven't actually yet spoken about this.
But it's not in terms of the coronavirus.
I think this paper was written before the coronavirus was a thing, so it's not to do with the coronavirus. No, thankfully not.
Very predictive, huh? Predictive power.
Statisticians knew this was coming a long time ago with their terminology. That's right.
Right. So what is it here?
Okay. So what we have here is, first of all, we have a loss function. So this L you can see here is a loss function, and we're going to assume that this is the mean squared error loss function, or least squares loss function. So this is how L is defined here. And the population risk is essentially just the expected loss over the distribution of the data. So remember that we're assuming that there's an underlying distribution of the data, which is denoted by rho up here. So we assume that our data is generated according to this underlying distribution. And what we really want to do is to find a neural network that minimizes the population risk. So if you average over all possible data examples that you're likely to see, given this underlying distribution rho, then compute the average loss over that data distribution. And that is the population risk. So the population you can think of as all of the possible data examples. And we want to average our loss over all of those possible data examples. Does that make sense? So the population risk is a function of the network parameters theta. And here just above, you can see he's capturing all of the AKs and the WKs into theta. So it's a function of the network parameters. So we vary the network parameters, we get a different model, and of course our loss will change given a certain input. And the population risk is just the average loss over all of the data examples. Now, this is the thing we'd like to minimize. So this is a kind of central point, I suppose, in machine learning. So this is the thing that we actually want to minimize. We really want to minimize the population risk. So the loss over all possible data examples that we could ever see. But of course, we can't do that because we don't have access to Rho. First of all we have is a finite data set to work with. So we just have some sample from this underlying distribution Rho. So even though this is the thing that we really want to optimize, in practice, this is the thing that we actually optimize. So this is the empirical risk, and you can think of it as an approximation, if you like, of the empirical risk. So what we really have in practice are n data samples, which we're going to assume are independently sampled from this underlying distribution Rho. And we want to minimize this empirical risk, which is just the average, again, the average loss over those data examples, just over this finite sample that we have. So this thing we can actually compute. So we have our model, we have our data, we have our n data examples. This is a finite computation, so we can compute this. And this is the thing in practice that we actually want to minimize the empirical risk. Okay. Just a further couple of definitions before I go to the theorems. So here's one of the norms I was mentioning earlier. So I mentioned the path norm is what they use for regularizing, and this is the definition of the path norm. So it's a measure of the complexity, if you like, of the neural network. So remember that AK and WK are the parameters of the model, and we're going to compute the path norm like this. And you can think of this as just a measure of how wiggly the network function is. So if you had AK and WK as being very large, then in principle you could have a very complex, very complicated function for the network. In which case you get a very large path norm. So small path norm typically means simpler functions. So given that measure of complexity, what we do again in practice is we will minimize the regularized empirical loss. And so this is the object here that he calls the regularized risk, or the regularized empirical risk. And it's the same as the empirical risk, just with this extra added term. So we're going to add a regularization parameter, lambda, times the path norm. And this +1, you can kind of ignore this. As you can see here, he just says that we're adding this +1 just to simplify the proof. It's not important. You can imagine this just without the +1. But you can see what the point is here. We're adding an extra term to our loss function, and this term will penalize large values of the path norm. So if our network function is very complicated, very complex, then this is going to add a lot to our loss, and we don't want that. So we want to keep the path norm relatively small. And the regularization parameter, by the way, lambda, is always positive. So this is always going to be an extra positive term that we're adding onto the loss function. Okay, and so given all that, the regularized estimator, so the parameters that we actually want to find, or we actually will find, are given as the argmin of j sub lambda. So this is what we're going to denote by theta hat, and we've got a subscript for n, the number of data examples, and lambda, the regularization coefficient as well. Any questions? So that's pretty much all the preliminaries, all the notation, definitions, and so on. So hopefully everyone's up to speed with this so far. Any questions? Okay, good. So I'll come back to the Barren space section in a minute, but I think before I do that, I wanted to have a quick look at the statement of the theorems, just to see what is shown in the paper. And we'll come back to look at what these Barren norms and so on are in a minute. So the first theorem I want to point out is theorem 3.1, which, as you can see, is an approximation theorem. So we'll come back to what these things are and the definitions of these in just a minute. But just for the moment, this script b sub 2 is a function space. So x is our input space. And so all we're saying here is that for f belonging to some function space, so this is going to be our target function belonging to some function space, there exists a two-layer neural network. So there's a particular value of theta, the parameters, we're going to call it theta tilde, such that the population risk is bounded by this quantity. And on the right-hand side here, you can see on the top we have some gamma object. This is just the norm. This is the function space norm of the target function. So again, it's another one of these norms that's just going to be floating around in this paper. We'll see the definition of this in just in a moment. So it's this is a constant value, right? So remember that the target function is fixed. So this is some constant, and m is the number of neurons in the hidden layer. So this first equation says that if the target function belongs to some function space, and that function space is going to be reachable, or the target function will be reachable by our neural network, then the neural network can, in principle, get arbitrarily close to that target function, in the sense that the population risk is converges. It converges to 0 as the number of hidden units goes to infinity. So as m becomes large, then the population risk will shrink to 0. So that means that we're approximating the target function. And the second part of this, which is quite an interesting extra inequality, is that the path norm is bounded again by some constant. So this again is this function space norm of the target function, which is just constant, right? So whatever m is, this path norm is constant. And that may be quite surprising at first, because you'd think that, okay, well, as my number of neurons in the hidden layer goes to infinity, I may expect that the path norm will just blow up, which it could well do. But what this theorem says is that you can find parameters such that this wider and wider network converges to the target function in such a way that the path norm doesn't blow up. It stays bounded by this constant here. So this is quite a nice result. So it means that the function is not overly complex as the number of neurons goes to infinity, or at least you can find a function, a neural network with arbitrarily large hidden layer, where the path norm doesn't blow up and the function doesn't become overly complex. So that's a good thing, because it means that we stand a good chance of not overfitting in that case, if we can bound that path norm. And that's what we'll see later on in the paper. So this is the first main result, I'd say, of this paper, is this approximation property. Are there any questions about this? Okay. The other two theorems I want to point out before I jump back to the definitions of the Barren space and so on. Theorem 4.1. So this is a bound, again, as you can see, on the population risk. So the statement of the theorem says, okay, we have the target function f star, and we're going to assume that it belongs to some function space, this Barren space, and we're going to assume that we've found some lambda n. So this is going to be some function of the number of data examples, and also the dimensionality of the input space. In fact, you can see lambda n is defined just here. So there's lambda n. So given that our regularization parameter that we use, lambda, is greater than or equal to lambda n, then we have a convergence estimate for the population risk. And so this is what the convergence estimate says. And it's in two parts, really. So the first two terms you can see here on the top are related to the approximation error. So the first term you'll recognize looks kind of similar to what we see up here. So again, this is basically saying that as the number of hidden units goes to infinity, then our network can get arbitrarily close to the target function. But we're also putting a regularization parameter on our loss function. So that's going to affect the function that we find. And so the approximation is impacted by that choice of regularization parameter, which is why you get this extra term on the end here. So if you had lambda equal to 0, then okay, you can get arbitrarily close to the true target function, as we've seen up here. But in practice, if you just set lambda to 0 all the time, then you're likely to blow up. So this control, if you like, over the regularization parameter ensures that you have this kind of bound where the approximation error is controlled like this. The second two terms on the second line here is what he's calling the estimation error. And this is down to the finite sample that we have from the data. So if we take a look at the statement of the theorem up here, So it says that assume our target function f star is in our function space. We've set some bound on our regularization parameter, so it's suitably large enough. Then for any delta, with probability at least 1 minus delta over the choice of the training set S, we have this. So so there is noise, of course, in the sampling of the finite data set. So we only have n examples, and again, that has to impact our ability to find the true target function, because we don't see all possible data examples. We only have a finite subset, and of course it does. And the sampling of that data set is a random process. We're assuming it's a random process. It's been randomly sampled from this underlying distribution rho. So this is why this is a probabilistic estimate. So for any delta with probability 1 minus delta, we get this extra term on the end here. And this is down to the noise in sampling from the data. But as you can see, that noise shrinks to 0 as the number of data examples goes to infinity. So as we get more and more data, then the uncertainty due to the finiteness, if you like, of the data sample that we have decreases. So this term will go to 0. And again, this term here is just the Barren norm of the target function. So this thing is a constant. So this whole thing is just order 1 over root n. Okay, so that's the main result of this paper for the noiseless case. So this is just the case where we assume we have inputs and outputs, xi and yi, and that yi is equal to f star of xi. So there's no noise. So it's just an exact mapping, and we just want to learn the exact mapping. So this is the estimate we get in that case of no noise. An analogous result theorem appears later on for the noisy case, which is theorem 4.2 here. And as you can see, it's a very similar looking theorem, but we do have extra terms in the end of this estimate, again, just to account for the fact that there is noise also in the labels that we're getting. So the yi's that we're training on are a bit wrong, and we know that. And so this term adds to this estimate, so it accounts for that noise in the labels as well. Good. Any questions about any of these theorems? Those are the 3 main results of the paper.
Well, can you remind me what was the number of neurons?
The number of norms, yes. So we have
neurons.
Number of nodes.
Sorry, neurons.
Oh, neurons. That is m. So m here is the number of neurons in the hidden layer, and n.
Oh,
yeah.
Neurons in hidden layer.
Yeah. So imagine that we have the neural network. So we have our inputs x. Let's say our inputs are just 2-dimensional, just as an example.
So the number of layers, hidden layers,
is 1.
Oh, it's only 1.
Exactly. Yes.
Okay. Now for the first theorem, noiseless, if I want to pre-understand or the noisy case, I can look at the noiseless theorem and put a very, very tiny noise, and to see what change that will do to that nice form 4.2 or 4.1.
I'm not sure I follow what you mean.
Okay. First of all, I need to connect all this to the Monte Carlo that is not mentioned. It's mentioned few lines before, but I think you skipped it.
Yeah, I'll come back to that in a minute.
Okay, so I'm aiming to find connection between the noise as a form of regularization, okay, which is not the mainstream thinking. Because you see, there is a notion, sorry if I'm taking you from the paper.
No,
There's a notion that sometimes with clever use of noise, you can reveal the signal. Okay, there are situations like that.
But it's not mostly noise in the inputs. I think people use that for, though, right?
Yeah, so the noise can be a tool to discern the signal. So now the regularization
Regularization.
is also a tool here,
Mhm.
because when you put some kind of penalty, you contain the scope of many results, right? You put a cap on
Yes.
things. So maybe I'm not too clear because it's early in the morning here. I just woke up half hour ago, but with all my jumble, maybe you can formulate what I'm trying to say, if you can do that.
Okay, so you want to argue that the output noise, the noise on the labels, can also act as a regularizer,
And vice versa.
okay, and what does that mean for the connection between theorems 4.1 and 4.2?
Because what? Oh, the 4.2 has 1 over square root n, which I connect to the Monte Carlo, which brings you to the probabilistic terms, right?
These terms at the end here.
Yeah, that's kind of signature of, for me, Monte Carlo. Maybe I'm mixing up things, so.
Yeah, it's not clear to me. I need to think a bit more about that.
Okay.
It's an interesting comment though. Yes, that I've never thought about that before. That the noise in the output labels kind of act as in a way as a kind of regularizer. Yeah, it's an interesting comment. Yeah, I'll think a bit more about that. I don't have a good answer for it at the moment.
Okay.
Okay. Yeah. Good. Thanks. So anyway, so those are the main theorems, and I just want to maybe for just the last thing for today at least is to go through the definitions of the Barren space and the Barren space norms. And I wanted to, if we can make it, to talk a little bit about this connection with kernels, which as I said, as mentioned before, I found quite insightful. But first of all, the Barren space.
Sorry, Kevin, could I ask a quick question?
Yeah, of course, please.
So in these theorems, the M, because we're in the one hidden layer setting, really this is a proxy for the number of parameters.
Yes, it is. I mean, it's directly controlling the number of parameters, isn't it? So M isn't actually the number of parameters, but it's the number of parameters is a
yeah. My thought is what would happen if I have multiple hidden layers? Then as I add neurons, I don't get a linear relationship to the number of parameters.
Yes, good question. So that's not counted by this paper at all. But this is what he takes care of in a follow-up paper. If you have multiple hidden layers, what happens then? But yeah, this paper isn't going to treat that. It's kind of already enough complexity, I find, just to think of the two-layer case, the single hidden layer. But I think in the single hidden layer case, for me, the connection to kernels is maybe a bit more immediate. You can kind of see it a bit clearer. But there is still a connection in the deep network case as well, but it's not treated in this paper. So I can't really give a good answer to that one until we or if we take a look at the follow-up paper later on.
Sure, thanks.
Okay. So anyway, so the Barren space. So the Barren space is a function space, and this is the space that the neural network is going to be living in. So this space is constructed in such a way that all networks of any width are contained in this Barren space. And this is a very large space, and as you've seen in the statement of the theorems, we assume that the target function is going to lie in this space, which feels like not a very controversial assumption, at least. It's going to be because it's so powerful. It's arbitrarily close to any continuous function and so on. So it seems like not a terrible assumption to make. But the Barren space is the function space that the neural network is going to be living in. So let's take a look at this. So he defines a few more things. So first of all, we're going to constrain the weights W to have one norm. Unit one norm, put it that way. Again, I think this isn't actually essential. This is just to help simplify the proofs later on. Of course, you can do this without loss of generality, right? So you can always absorb the any coefficient multiplying W into the parameters A, because the activation function is scale invariant. So this is without loss of generality, but it's going to help a lot with the proofs again later on. And we're going to consider probability measures on the weights effectively. So the weights are constrained to the unit one norm, and we're going to consider a probability distribution pi on those weights W. Now, given that, let's think about the collection of functions which have this form. So you can see we're already kind of getting a bit closer now towards the neural networks. So pi is this distribution on the weights W. We have the same activation function sigma, the same form here, so an inner product between W and X. So X is the inputs, and we have some function here A, which is also a function of W. And we just average over all of the possible weights W, if you like, according to this distribution pi. So this is the form of the function that we're going to be considering, and this form of function includes neural networks, because of course we can choose pi to be a sum of delta distributions, and if we do that, then this integral here will just turn into a sum. And we recover exactly what we had above in terms of the formulation of the neural network model. So you can think of this as encompassing all possible neural network functions just by choosing a suitable distribution pi. So for any finite width, we'll just have a sum of, let's say, m delta distributions on given weights, and that will give our neural network function for a finite width. So this is the general form that we're going to consider. And the norm in this function space is shown just down here. So we have p norms for p greater than or equal to 1. And yeah, this is just the definition here. And it's given as an infimum over all a and pi belonging to this set here, which is defined just below. So what does this mean? Well, it means that, okay, for a given function of this form, there may be many possible functions A and distributions pi for which give the same function. So we're just going to choose the one that gives us the infimum of this quantity here, and this is just the average, if you like, over the function A. So this is the definition of the Barren space norm for every p. Any questions about any of this stuff? So the first time we see this definition, it seems a bit knotted, but it's not too bad. I mean, this is the general formulation of the function, and the Barren space norm itself is okay. It's just we have to just remember that there's this infimum here, so we're always choosing the a and pi that gives us the smallest value of what's in it. Okay. So the Barren space then is just all of the functions of that form for which have a finite Barren norm. And as we mentioned before, that this is going to include all neural networks as well. Okay, so a couple of properties of the Barren space. So due to Holder's inequality, we do have this relation between the Barren spaces for each p. The one here is script b sub 2 is a particularly interesting one, and actually you will have seen in the theorems earlier that I showed just earlier on that this is actually the function space we're going to assume the target function lives in. Each of these Barren spaces for any p are all extremely rich function spaces. So as you can see here, all of them are dense in the space of continuous functions. And he also makes the comment here about the two-lane neural networks all belong to this Barren space as well, because we can just choose the pi as a sum of delta functions in this way, and then we recover that equation for the two-lane neural networks that we had before.
a mischievous query here would be the definition looks at the beginning a bit arbitrary, although you justified it. And of course, by its form 1 over p, it aims at using later on Hilbert. But suppose Hilbert didn't exist. How could we achieve the goal that comes there in small letters contained in sequence of B's, capital B's, B infinity and so on and so on. So that goal, what is it? When I say capital B infinity of X included in that sequence and finally in B1.
Yeah, so what's the question, sorry?
What's its purpose?
Oh, well,
this sequence of containment of the in B's.
Well, I mean, at this point, you can just take it as a statement of fact, just something that is just true and follows from Hilbert's inequality. In this paper, the only Barren spaces that are actually used are the last two, so B sub 2 and B sub 1, and this inclusion is used further on down as well. But these are the only two norms that are used. So B2 comes about, I think, because we're particularly looking at the mean squared error loss. Was one of the proofs later on. You'll see how this function space naturally occurs because we're using this mean squared error loss. I think that's the main reason why this one is in the statement of the theorems. And this B1 function space comes up because of the definition of the path norm. And again, you'll see it later on in some of the theorems that this particular Barren space norm occurs quite naturally in relation to the path norm. So we have these two norms cropping up in the theorems, and it becomes useful to bound one norm by the other norm, which is why this conclusion becomes useful.
Okay, great.
For all the other P's are not actually used at all. So otherwise, you can just take this as a statement of fact.
Sure.
Okay. Yes, okay, so all of these Barren spaces for every P are all rich, as I say, dense in the space of continuous functions. And you can see that the way he says that here is due to the universal approximation theorem of neural networks. So we know that given the neural network belongs to this function space, we know that the neural networks have this universal approximation property, and therefore the Barren space itself is very rich, and we can approximate arbitrarily close any continuous function. So this is a big function space. This paragraph here is a statement about relating the Fourier transform of a function and the infinity norm of the Barren space. Now this paragraph isn't used anywhere in this paper at all. To be honest, I haven't looked at these references. I don't know too much about where this comes from. But this particular statement isn't used at all. I think he just wrote it down because it's quite an interesting and important fact in general. But we're not going to use this. We don't use Fourier transforms anywhere in this paper. Okay, probably the last thing I want to talk through is this section here, the connection with the reproducing kernel Hilbert space. So, as you can see, he writes the Barren space has got a natural connection with the RKHS. And this gives us some kind of insight into the performance of neural networks as opposed to the performance of kernel methods in some cases, that the neural networks can outperform kernel methods, and it gives a kind of hint as to why this might be the case. So first of all, to see this connection, he defines this set of functions here given by script h sub pi, and as you can see, it looks very similar to the definition that we had above. This is a typing mistake here, by the way. This alpha should just be an A. So this is the form of the functions that he's considering here with respect to this norm. So this is a norm on this space, and it's just the expected value of A, or the L2 norm of the function A, if you like. So there's a reference here, which is where they prove that this function space with this norm is in fact the RKHS with respect to the kernel defined by this equation here. So this kernel is a regular kernel function of two variables. It's symmetric, it's positive definite, and so on. And it's given by this expectation over this quantity in here, which, as you can see, is related to the hidden layer of the neural network function. So if we just take this equation of 3.5 as a definition of the kernel function, then we know that, let's assume that it is a kernel function. We know that the kernel function defines an RKHS, and that RKHS is characterized according to this definition at the top here. So this is a result proved in this reference number 37 here. And you can see now already we have some quite strong connection coming in with the Barren space. The difference here is that this distribution pi is fixed, right? So what we're defining a kernel K, and you can see we've got a pi in the subscript here. So given a distribution pi, we can define a kernel function by equation 3.5, and then this kernel function is a fixed kernel function, the distribution pi is fixed, and it defines a set of functions of this form according to this norm, and this is the RKHS. So given that, we can see that the Barren space that we defined above, in fact, is just a union of all of the possible RKHS spaces for different distributions pi. And that's what you can see written down here. So the Barren space can be viewed as a union of a family of RKHS with kernels defined by different choices of pi through equation 3.5. In other words, the Barren space is defined by equation 3.6 here. So we already know that the RKHS is potentially a very rich function space, depending on the choice of kernel. And here we're saying that the Barren space is actually much, much richer than that, because it encompasses all kernels of this form for all possible choices of this distribution pi. Okay. In section 4.1, so he kind of continues this thought train a little bit. So in section 4.1, let's think about, for example, a target function f star, which belongs to the Barren space B sub 2. So this is the Barren space. Let's just have a quick recap again where it comes from. So the Barren space B sub 2 is defined by the norm here with p equal to 2. Okay, so if we assume that we have this target function in this Barren space, then okay, so we choose an a star and a pi star, which represents this function f star. Remember that the norm is defined as this infimum, so we choose the one that is attaining this infimum. Then the Barren space norm is given by this. So this just follows from the definition above, right? So we have the Barren norm squared, if you like, of the target function is just the expectation over this distribution pi star of this function a star squared. Okay, and so what does that mean? Well, it means that f star takes this form. So we've chosen an a star and a pi star that characterize this function, that achieve this infimum, and that means that the target function f star is of this form, the top line of equation 4.3. And so now what he says is, okay, well, what if we consider a different distribution pi 0? Well, if we take pi 0 to be a distribution such that pi is absolutely continuous with respect to pi 0, then we can write f star in this form, where we have here d pi star by d pi 0. This is just the Radon-Nikodym derivative. So this is now the representation, if you like, of f star in terms of the distribution pi 0. Okay, so what if we then think of the RKHS space, which is defined by the kernel that uses the distribution pi 0. So that's this guy here. So this here is the RKHS with respect to pi 0. And the kernel function that defines that RKHS is given just here. Well, what do we know about this RKHS? Well, as it said up above, the norm of the function f in this RKHS is given by this equation. So that means that the norm of our function f star in the RKHS h pi 0 is given by this equation. Oops, this equation here. Okay, this just follows from the representation we have in 4.3. So the point here is that this quantity may blow up depending on how pi 0 and pi star are related. So we could choose our target function f star in such a way that it belongs to this Barren space, and the pi star that defines it is, let's say, a delta function. Let's say it's just a single neuron. It's a network function which is just a single neuron. In fact, that's the example he gives down here. What if we choose a target function of this form? So pi star is just a single delta function. But we could take pi 0 to be something quite different. So pi 0 could just be the uniform distribution over the space where the weights live. So these are very different distributions over the same space, and we know that the quantity you see in this equation here will blow up. So this norm will be infinity. The RKHS norm of f star will be infinity, whereas the Barren space norm of the network function will be finite. Okay, so this is an interesting observation because these a priori estimates of the kind that we're looking at in this paper are always given in terms of the norm of the target function. So he references here another paper that proves similar results to this one, but this paper is looking only at kernel methods, that the population risk scales like this. So this is a similar rate, or actually the same rate, proved in this paper. But the difference is the norm is the RKHS norm. So what happens if the RKHS norm blows up? This estimate becomes vacuous, so it becomes meaningless. And this is actually what happens in this example down here. So it gives an example of a target function f star, where the Barren norm is finite. In fact, as you can see here, the Barren norm of this target function is equal to 1, but the RKHS norm is equal to infinity. That means that the convergence estimate of the population risk is meaningless. If we use that kernel and we work in that RKHS, then the convergence estimate is meaningless. But the convergence estimate that he gets in this paper holds. So we get a much better convergence using the neural network, using the Barren space norm, than we do in the RKHS using the RKHS norm. And in the final example, what he does here in this example is basically demonstrate that. So he picks this target function. Of course, this is a completely contrived example just to demonstrate the point. But he picks this example where the Barren space norm is 1, the RKHS norm is infinity, and then run some experiments to try to find these models, the neural network models and the kernel models, and to see how those models' convergence scales with the number of data examples. So assuming the population risk, as you can see here, scales like this with some beta. What is beta? So this doesn't tell us anything anymore. If this norm on the top is infinity, this doesn't tell us anything. So what is actually this scaling behavior for the RKHS, for the kernel method? And what you can see in this table down the bottom here is that the kernel method gets worse and worse as the number of data points gets larger and larger. So the scaling becomes really bad. Whereas the neural network scaling more or less stays the same. And in fact, you can see the beta we have on the top row here is actually better than the one in the statement of the theorem that he makes in this paper. So this took me a little while to get my head around what's going on here, but I found this very interesting, very insightful, because this does demonstrate the benefit, if you like, of using neural networks over kernel methods. You can come up with examples, you can see examples where it's clearly the case that working in a particular choice of RKHS could be really, really bad, depending on the target function that you're going for. But because the network can effectively learn the kernel, it can learn the weights. That means it's able to adjust this distribution pi. it can find a function whose norm is much smaller. And as we can see by the convergence estimates, this means that the scaling with respect to the number of data examples is much nicer. So I thought this was quite a nice section, and I think it's probably a good place also for me to stop at this point and to let things sink in. So I won't go any further in this session. I think that's probably going to be enough for now.
Yeah, thank you. Yeah, that's very, very deep actually what you are saying here. It's interesting.
It is. Yeah. Well, I thought it was a good place to stop.
Yeah, exactly. I think I need to digest because it's interesting because I mean, as you know, I'm working on this Kernel flows method, and there is no actually clear justification for the convergence of this method.
Yes.
And but then there is an adaptation of the parameters of the kernels, which I think could be related to what you have been saying here, right?
Yeah, maybe.
And I also was looking, actually, there was this conference last week. I don't know if you attended it, but the information theory at Imperial. And there was some guy who also argued for the neural networks, Emmanuel Abbé from EPFL. So I posted the paper on the chat, and he was also arguing that yeah, neural networks, I mean, they are richer than Rkhs, and then he even constructed some functions that are learnable using neural networks, but they are not learnable using kernel methods. I don't know. Do you know this paper, Kevin? The one I put on the archive?
Maybe you can send me the link.
Yeah, I will send it to you by email. Yes.
Yeah, that'd be good. That'd be good.
Yeah. Yes, it's, what you are saying is consistent with just this paper that I found last week. And then he gave a short talk at this information theory seminar conference at Imperial last week.
Okay, yeah, I missed that. It's a shame. I
think but they are recorded. They are on YouTube. Yeah.
Okay, nice. Yeah. But I think this, the real situation is even subtler than this, though, because the problem is with neural networks. In principle, yes, you do have you encompass all these RKHS spaces, but for any finite width neural network, the distribution pi has to be a sum of delta distributions. And so that in itself, like the space of all possible delta distributions, isn't that rich, right? You can come up with crazy distributions, which this is a really poor approximation. But it's just that as you increase and increase and increase the number of neurons in the hidden layer, you can get better and better approximations for whatever distribution you have there. But that comes at a cost, because one thing that this paper doesn't talk about is training these networks. So how do you actually find these solutions? This paper proves that these solutions exist and that they give you a nice convergence rate with respect to the number of data examples. But it kind of skirts around the issue of how you actually find them. And I think it's the case that as the number of neurons goes to infinity, it becomes harder and harder to actually find them, because training these models becomes more difficult. And that's probably a subject for another time. But I think there's a lot of subtlety here about working with these models.
Yeah, no, that's I think we think deeply more about this.
Yeah. Great. Well, as I say, I think I'll probably stop at this point.
Yeah, thank you very much. Yeah, thank you. Yeah, any other questions from the audience?
I'm keen to get just general feedback on what people would find interesting. As I mentioned at the beginning, I don't want this to be a talk or a series of talks, really, more a kind of discussion and heading in the direction that everyone finds interesting.
Yeah, I agree. I think it would be nice. Actually, for me, I would be interested in getting deeper into this connection between neural networks and kernel methods, limitations of kernel methods versus neural networks. That's that seems to be like a nice thing, actually.
Yeah, I think so. Well, I mean,
anyway, we have to say. I also liked Itamar's comment about the knowledge playing the role of regularizer. That was like nice. I don't know. I think it also requires more thinking, I guess. Yeah. Definitely. Yeah. I'll go away and think about that one. That was a good comment. Yeah. Okay. Good. But well, maybe we can leave it there for today. And I don't know if we can discuss offline about what people find interesting next. But I mean, audience, we are free. Feel free to contact me and Kevin. And if you have suggestions. Again, we are playing it by ear, so we are quite flexible here. We just want to learn things together. So yeah, if you have a particular direction you want to explore, just let us know, and then we'll take it from there. Yeah.
Okay.
But even if you yourself, I mean, if you are in the audience and you want to present something, I mean, just tell me. I mean, I'll be happy to schedule you for a session as well. Yeah.
Yeah, absolutely. I mean, it'd be not, that's kind of the ideal. I think really would be to you know, all contribute, collaborate, pile in on this one. It's
yeah,
that'd be nice.
Yeah. So I posted this article on the chat. As I said, I became aware of it just last week. I think that will be actually nice. I would be interested in reading and learning about it. I don't think I'd be able to present it, but I think it would be nice to explore it a bit further.
Yeah, absolutely.
Yeah.
Good. All right. Well.
Yeah. All right. Okay. Thank you very much, Kevin, and thanks to everyone. Yeah. Take care. Yeah.
Yeah. Thanks, everyone.
Yeah. Thanks. Bye. Bye.